Let us just wait for 2 more minutes before starting the session to see if somebody else is joining. Okay, so I welcome all of you to the 11th live session of the course Introduction to Fluid Mechanics, which is being offered by Professor Suman Chakrabarty of IIT Kharagpur. And as in for myself, I am Abhik Dev, and I am doing my PhD in the Department of Mechanical Engineering at IISc Bangalore. And in today's session, we shall be dealing with the problems related to the Navier-Stokes equation, related to the derivation of the Navier-Stokes equation and its and some of its forms, or the solution of the Navier-Stokes equation for certain special cases. So um, mm, at any point of time, if there is any doubt, you can interrupt and ask. Uh, so uh, yeah, let us begin today's session. We will continue with one of the problems that was the concept of which was started in the previous class itself. That is the Reynolds transport theorem, its application on a accelerating body, or the Reynolds transport theorem applied for the conservation of momentum for an accelerating body. That we will be doing, solving one of the problems related to that, and then we will move on to other problems related to the Navier-Stokes equation and its solution. Okay, so a vane is attached to a block as shown in the figure. The block moves under the influence of a liquid jet, and the mass of the block is mb. So the coefficient of kinetic friction for the motion of the block along the surface is mu k. Obtain a differential equation for the speed of the block as it accelerates from rest. So this problem, so this block of mass mb, it is sliding on a plane such that the coefficient of friction is mu b. So there is a frictional force opposite to its movement. ub is the velocity of the block, which is a function of time, that it is changing with time, that it is accelerating. There is a vane like this from which a liquid jet is passed into the a liquid jet is passed at a velocity vj and an area aj. Okay, so for this we considered a control volume that is moving with the block itself. Okay, so we considered this as the control volume which is moving, but it's which is the control volume, it is also moving at a velocity ub, but its shape or dimensions are not changing with time, that is its volume is fixed with time. So it is like the first term on the right hand side of the momentum conservation will become 0. Now writing the x momentum conservation equation, for a control volume that is moving at velocity ub as a function of time t, that is the control volume is accelerating. So sum of the forces in the x direction minus there will be a component, a relative acceleration and dm. This component will come because the control volume is accelerating. Then ddt of integration control volume rho u dv plus integration control surface rho u ur dot n cap dA. This is 0 since control volume is not deforming or changing the volume with time. Okay. Now what is fx? So we are considering this as the positive x direction, this is positive y direction. So the friction will act opposite to the considered positive x direction, that is along the negative x direction, and the friction force Fr will be equal to mu b cross mu b multiplied by mb into g, mu b multiplied by mb into g. So this is mu b multiplied by mb into g. Mb into g is the weight multiplied by mu b, which acts to the negative x direction. Okay, so we will have to write it as minus of mu b mb into g minus what is the relative acceleration. Relative acceleration will be change of ub with respect to time, that is dub by dt, and the vector sign, so we are considering only the x direction acceleration, so it is only ub. So minus of dub dt integration control volume of dm, which is the mass of the control volume, that is mb, that is mb. Okay, and the first term is 0 on the right hand side, 0, and the only mass is coming in, there is nothing is going out. Okay, but with respect to the control volume we have to see so what is it with respect to the control volume? So you see that the jet, if we draw the jet like this, it is striking at Vj, but the yeah, so and this block itself, it is moving at a velocity u b. Okay, so the velocity, the resultant velocity with which which is responsible for the mass entering into the control volume. So this m dot, if we write it, so m dot, that will be equal to rho aj vj minus ub. This is the mass entering into the control volume. And then what is the this is the mass entering into the control volume, and we have to write uh, mm, at what is the velocity of the jet relative to the control volume. So this is the mass entering into the control volume, and u r that will give us the velocity relative to the control volume, that will be um, uh, minus of, not this one, it will be minus because of the inlet, and ur will be vj minus ub. Okay, this is the relative velocity. The relative velocity of the jet, uh, relative velocity of jet with respect to the control volume, and this is the mass. See, the entire mass is the mass that is coming because of the jet is rho aj vj, but since that velocity vj is not actually responsible for the entry of that mass into the control volume, the entry of the mass will be because of vj minus ub. So it is like so the mass is it is around vj is say 10 meters per second, and ub is 3 meters per second. Then at every second, mm, so the velocity with which it will strike, or we can say that if the block is stationary, then how much of the water jet will get into the mm, region, control volume region per second, it will be 7 meters, that is 10 minus 3. So the mass that is coming into the control volume will be that is due to this Vj minus Ub. So that is why, so this is minus of m dot e into ur. Okay, so this comes up as so m dot in is this one that we have calculated, and this is um the ur, that is the relative velocity of the jet with respect to the control volume. So this is minus of mj is rho aj vj minus ub into vj minus ub. Okay, so this is minus of rho aj vj minus ub whole square. Therefore dub by dt, we are taking to the we are changing the side, so we are taking this to the left and right hand side. So this will be uh, rho aj vj minus ub whole square by mb minus of mu b into g. So this will be the expression for the speed of the block as it accelerates from rest. Expression for the speed of the block as it accelerates from rest. Okay, so yeah, that is option number C, right? Yeah, Option number C. This is the correct answer. So if you have any doubt in this, you can ask. Okay, so we will move to the next problem now, which will be essentially a the related to the Navier-Stokes equation and its application, some of its applications. So for the derivation, the concepts are related to the derivation of the Navier-Stokes equation from the differential analysis. And also the uh, solution of the Navier-Stokes equation for some of the problems like flow through the pipes, for flow through pipes. So Yes, so first question is related to the components of stress on a fluid element. So we know there are two components of the stresses. One is the deviatoric stress, one is the hydrostatic stress. So the hydrostatic component of stress on a fluid element is independent of the deformation in the fluid element. The deviatoric component of stress on a fluid element is independent of the deformation in the fluid element. The mechanical pressure represents the effect of translational mode of energy of the system of molecules, and the mechanical pressure represents the combined effects of translational, rotational, and vibrational modes of energy of the system of molecules. So, which of these following statements is or are true? For this, we have to uh, mm, it's better that instead of going directly into the solution, we go through the stepwise solution of how it is coming. So the Cauchy's equation of motion is given as rho dy dt is equal to rho gi plus dou by dou xj tau ij. Okay, so this is the Cauchy's equation of motion. The Cauchy's equation of motion we have uh, um, arrived to by applying the momentum conservation to a differential control volume. And from this step we will continue. Okay, so this stress, the stress on a fluid element tau ij, that is equal to minus p delta ij plus sigma ij, where delta ij is called Kronecker delta is equal to 1 when I is equal to 0, sorry, when I is equal to j is equal to 0 when I is not equal to j. Okay, so and so this p delta ij is called the p delta ij. This is called the hydrostatic stress, and it takes the form of something like this in 3 dimensions: minus p 0 0 0 minus p 0 and 0 0 minus p. That is essentially an identity element, where identity matrix multiplied by this element minus p, and this sigma ij is the deviatoric stress component. Okay, it's called the deviatoric stress component. This hydrostatic stress is independent of the deformation, because there is no deformation element shown here, right? Hydrostatic stress minus p delta ij is independent of deformation of fluid element. And this sigma ij we have to find out now. So for the sigma ij, before we go into this, del ui del xj. Okay, this is equal to half of del ui del xj plus del uj del xi plus half of del ui del xj minus del uj del xi. Right, these two terms gets cancelled, so this is coming to this one. Now this can be written as eij. This term del ui by del xj plus del uj by del xi, half of this is the strain eij, and this is half of gamma ij. Okay, now for Newtonian fluids, just a minute. Okay, for Newtonian fluids, this sigma ij, that is the stress, is proportional to the strain, shear strain. We can write it as sigma ij is equal to k I j m n e m n. Okay, this is the deviatoric stress component. Okay, and this is the isotropic tensor. Which becomes minus mu, or which becomes mu for when we consider the Newton's law of viscosity. Okay, now this Kijmn can be written as lambda delta ij delta mn plus mu delta im delta jn. Okay, plus r delta in delta jm. Okay, any isotropic tensor can be expressed in terms of the Kronecker delta. Any isotropic tensor can be expressed in terms of Kronecker delta. Okay. Now this is sigma ij. Now sigma ji is equal to kji mn emn, but this sigma ij is equal to sigma ji. The two, that is sigma ij, will be equal to sigma ji. That is, the deviatory stress components are as we have seen previously that they are symmetric. Okay, they are symmetric. Therefore, Kij Mn is equal to Kj Mn. Okay, so if we write this and simplify it, we will get that from here. Okay, let me write it. So Kij Mn can be, we have written it as delta Ij delta Mn plus mu delta Im delta Jn plus R delta In delta Jm, and Kji Mn is equal to lambda Ji lambda Mn plus mu lambda Jm lambda In plus R delta Jn delta Im. So we are just subtracting it, minus 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 minus, subtracting. So this is 0, and this is also 0, since delta Ij is equal to delta Ji, and here we will get plus mu minus R delta Im delta Jn minus delta In delta Jm is equal to 0. But this term delta Im delta Jn and delta In delta Jm, this is not equal to 0. Okay, because if this becomes 0, then the entire Kijmn will become 0. Okay, so from here we will see that mu is equal to R. Now, therefore, delta sigma ij is equal to lambda delta ij delta Mn plus mu delta Im delta Jn plus mu delta In delta Jn. Sigma, this is Kijmn and multiplied by Emn. Now, this delta Ij, that is, the Kronecker delta, is not equal to 0 only when I is equal to j or m is equal to n. Okay, so because we are also considering delta mn. Okay, so this did not be written here. This is just yeah. So so only when this is equal to, so delta mn will be will not be equal to 0 only when m is equal to n. So I equal to j and m equals to n we have to put, so that we can now we take these terms. So lambda into delta ij delta mn emn this will not be equal to 0 when I equals to j and m is equal to n. Okay, so this will give us no, this is not equal to 0, so this term is not equal to 0 only when m is equal to n. So this becomes, therefore delta ij delta mn emn lambda, this actually becomes lambda into or let us consider the second terms first, not this terms. We are considering this term, uh, delta im delta jn and emn. So or just a minute. So this one, it will be lambda delta ij delta mn emn, so is equal to lambda into delta ij into emm. Since delta mn is not equal to 0 only when m is equal to n. So only when m is equal to n, this term will exist. Otherwise, this will turn to 0. So lambda into delta ij we are keeping, and e has to be become emm. Okay. Otherwise, if it is not emm, then the term will be entirely 0. Even in these cases, when I is not equal to j, this will turn to, the entire thing will turn to 0. But for if emn, for mn, if n is not equal to m, then also even if I is equal to j, then also it will turn to 0. So we are considering this term first. We are keeping the Kronecker delta ij for the time being. Now this one mu into delta im delta jn and emn. So this not equal to 0 when I is equal to m, and this not equal to 0 when j is equal to n. So this one will become eij, m will become I and n will become j. So this will become mu eij. Okay. Similarly, r delta sorry mu delta in delta jn emn is also equal to mu eij, or since eij is equal to eji. Okay, therefore the sigma ij will finally be lambda delta ij emm plus twice mu eij. And this tau ij, so this is a deviatory component, right? So the deviatory component, and you can see that this deviatory component is dependent on the deformation of fluid element. So the from here we see that the option number 1 is correct. Option number 1 is correct. that it is the derivative component is independent. This is not correct. Therefore, option number 2 is not correct. Okay. Therefore, if we go further, this therefore this tau ij can be written as minus p delta ij plus lambda emm into delta ij plus twice mu eij. Okay, or we can write it as for the timing we are keeping in this form itself. Let's say we keep in this form itself. And then normal stresses. Because we have been asked to go to the mechanical pressure. So the normal stresses I is equal to J. So if we put I is equal to J, tau I is equal to minus P plus lambda EMM lambda EMM plus twice mu EII. So EII and EII is equal to EMM. These are the same things, right? So this is equal to minus P plus 2 mu plus lambda EII. This P is the thermodynamic pressure. We take it to this side. So P is equal to minus tau II plus twice mu plus lambda EII. Sorry, this there will be this one. Delta ij. So this delta ii that we are taking, delta ii. So delta ii will be of what? Uh, uh, so delta ii, so it will be equal to 0, not equal to 0 three times. That is when I is equal to, that is when I is equal to 1, I is equal to 2 and I is equal to 3 is equal to, so delta ii will be equal to 3. That is how to say go about this. It is uh, that is I equals to j will happen thrice, right? For 1 1, I equal to j will happen thrice. That is I equals to j is equal to 1, 2 and 3. Okay, therefore for delta ij, if we take the magnitude, it will be just 3. Okay, so minus 3p, and this is 3p is equal to minus tau i plus this. this P is equal to minus tau II. Because we are for tau II, there are all the components, that is tau 1, tau 2, and tau 3. They are all included in this. But P we are taking only, that is, we are not taking separately as P1 plus P2 plus P3. If required, then we can assume this as in place of delta, this one we can assume it as something like this, delta 1 plus delta 2 plus delta 3 into P. Okay, so this will come, and this is like delta this becomes equal to what? This is equal to 1 plus 1 plus 1, that is 3, right? That is why this 3 is coming, by 3 plus 2 mu by 3 plus lambda by 3 EII. This is just a normal stress, EII. Okay, and this P is the thermodynamic pressure. And it incorporates thermodynamic pressure, it incorporates all the translational, rotational, vibrational modes of energy. Translational, rotational, and vibrational modes of energy. Okay, so the option 4, that mechanical pressure incorporates that, it is incorrect. Now coming to the mechanical pressure part, what will be the mechanical pressure? This tau II by 3 minus T tau I by 3 Pm is equal to mechanical pressure this is equal to minus tau II by 3, or if we expand this, it will be tau 1 plus tau 2 plus tau 3 by 3. This is the mechanical pressure, that is only due to normal stress components. This is the mechanical pressure. And it depends only on translational energy of molecules, right? Translational energy of the molecules, which is responsible for the normal stress. Therefore, P is equal to Pm plus lambda plus 2 mu by 3 sorry there is another delta Ij with the lambda also, right? So here also there will be another 3 coming for this. So this will be 3 lambda, and this will just be lambda plus lambda plus 2 mu by 3 to EII, and EII, that is equal to what? That is equal to 1 del U by del X plus del V by del Y plus del W by del Z for 3D, or this is just del dot V vector, or the volumetric strain rate, and this K is called the bulk viscosity. K. For incompressible fluids, del dot V is equal to 0, that is EII is equal to 0, that is P is equal to Pm, that is the thermodynamic pressure is equal to the mechanical pressure for all incompressible fluids. But if the fluid is not incompressible, but for compressible fluids, for P is equal to Pm, we invoke Stokes hypothesis, that is lambda is equal to minus 2 mu by 3. That is the Stokes hypothesis, right? In this case, for when lambda is equal to 2 mu by 3, then this term will also become 0. Lambda is equal to minus 2 mu by 3. So when lambda is equal to minus 2 mu by 3, so this term becomes 0 and P becomes equals to Pm. So for incompressible fluids, P equals to Pm by default, that is the thermodynamic pressure becomes equal to the mechanical pressure. But for compressible fluids, for the thermodynamic pressure to be made equal to the mechanical pressure, we invoke this Stokes hypothesis, that is lambda is equal to minus 2 mu by 3, and by incorporating this into the Cauchy's equation throughout, if we solve it, we will reach the Navier-Stokes equation in its most general form. Okay, so the correct option, the correct answer for this one will be, so 3 is correct. So the correct answer for this is 1 and 3 are correct. 1 and 3, that is option number A. Okay, so along with the solving the problem, we have also found out how we are relating, how we are reaching this Stokes hypothesis, or what is the requirement, because the requirement is that we have to reduce the number of variables for the solution of this Navier-Stokes equation. Okay. So if there is any doubt in this, you can ask. Okay, so going to the next problem. This was just a relationship between the mechanical pressure and the stress tensor components, which we have already discussed um, in the previous problem directly. So the answer is option number A. Now, which of these are is not correct about the Navier-Stokes equation? So they are valid only for incompressible flows. So nothing as such. They are valid for both compressible and incompressible flows because when we apply the Stokes hypothesis, the equation can be reduced. The number of variables in the equation can be reduced by invoking the Stokes hypothesis to reach the Navier-Stokes equation, which is valid for both compressible and incompressible flows. One number is wrong, as Navier-Stokes equation is valid for both compressible and incompressible flows. Okay, they are set of coupled second order nonlinear partial differential equations. Two number is correct. They are set of coupled equations because the velocity and pressure are coupled into a second order nonlinear partial differential equations. Set of uncoupled, no, they are coupled, so the option 3 is not correct. They are derived after taking into consideration the Stokes hypothesis, so 4 is correct. So 2 and 4 are correct, that is option number D is correct. Option number D is correct. So I hope this is clear to you. If there is any doubt in this, you can ask. So I request you to go through this problem and have an idea about how we will solve, uh, go about this problem, go about solving this problem. Okay, so there is this bearing, and there is one shaft in it which is rotating. Which is rotating at omega. Now this as the shaft is rotating, so this part is moving at a particular velocity. This part is stationary. Okay, and so in between these two, the viscosity will play an effect where the velocity will increase from 0 to this velocity v. Okay, now since this diametral clearance, which is, let's say, c, and the diameter is phi, is equal to 7.5 centimeter, whereas c is equal to 0.00635 centimeter, or rather twice c is this. So c is further than less, that is c is equal to 0.00317 centimeter, which is very less than phi, or the diameter. Therefore, we can model the flow of fluid between the bearing and shaft as flow between two infinitely large plates, infinitely large parallel plates. Therefore, from Newton's law of viscosity, the shear stress tau can be given as mu into du by dy, or mu delta u is v minus 0, and the distance between the two plates is c. What is mu? Or let us not give the values now. So v is equal to pi dn by 60. Okay, therefore this shear stress will be what? Therefore the shear stress is mu into pi dn by 60, that is velocity into c. Now this shear stress is acting on the diametral or on the circumference of the shaft and into the plane of the paper. That is it is 3.175 centimeter long, right? So in this dimension, L is equal to 3.175 centimeter. So the force due to shear stress is equal to tau into area, that is tau into this will be pi into diameter d into L. What is tau? Tau is mu into pi dn by 60 into c, and this multiplied by pi dl. So this comes out as mu pi squared d squared n into L by 60c. And therefore the torque required to overcome this force is T is equal to force multiplied by the perpendicular distance, because it is acting, the torque will be given with respect to the center. So the distance with respect to the force is R. So A or D, you can let me write it as D. Okay. Okay, so I don't know, somehow this whatever I have written is gone. So this is the center. This, at this point there will be this velocity acting, the velocity. So this is C, and diameter is equal to 7.5 centimeter, and the clearance is equal to price of C is 0.00635 centimeter, or C is equal to 0.003175 centimeter, which is very less than the diameter. Therefore we can model the flow between the bearing and shaft as flow between two infinitely long parallel plates. Therefore tau is equal to mu into du by dy, or mu into v minus 0 by c, where v is equal to pi dn by 60. Therefore tau is mu into pi dn by 60 c, and the force due to this shear stress Fs is equal to tau into area, that is tau into pi d into L. So this is mu into pi dn by 60 into pi dl. So it is mu pi square d square nl by 60 c. Therefore torque required to overcome this force T is force multiplied by R. Okay, so mu pi square d square nl by 60 c to d by 2, or mu pi square d cube nl by 120 c. So if we put the values mu is 0.0096, 0.0096 into pi square into d cube is it is 7.5 centimeter, so 0.075 meter cube to n is 3600 into L is, so in this dimension L is equal to 3.175 centimeter, so this is 0.03175 meter, 0.01375, sorry, 3.175, 0.03175 by 120 into the clearance. Clearance is this one in centimeters, so it will be 0.00003175, 0.000175 in meters. So if we put the values, what do we get? Point 0.0096. I don't know what is happening. Repeatedly causing problems. Just a minute. I think so. There is some issue. Just give me some time. I am trying to rejoin. So, okay, centimeter. equal to 5 centimeter, and twice of C is 0.00635 centimeter. So C is 0.00317 centimeter, which is very less than D. So we model the flow as in between two parallel infinite plates. Okay, so tau is equal to mu delta U by C. So mu into V minus 0 by C, and mu into, that is, pi dn by 60 C. And so just give me some time. I think so there is some issue with the connection. That is why it is repeatedly getting closed without saving it. Just give me some time. Okay, okay. So yeah, is in between two parallel plates, infinitely long, infinite parallel plates. Okay, therefore the shear stress is mu into V minus 0 by C. So mu by dn by C 60C. Then what we do, therefore the force F is shear stress into area, it is mu by dn by 60C into pi dl. So mu pi square d square nl by 60C. Therefore the torque T is equal to force into R, that is mu pi square d square nl by 60C into t by 2. So mu pi square d cube nl by 120C. If we put the values, 0.0096 into pi squared into 0.075 whole square into 3600 into 0.03175 by 120 into 0.0000317. So we will get this value to be 1.199 Newton meter, which is nearly equal to 1.2 Newton meter. That is option number C. Okay. Now going to the next problem. I request you to go through this problem and try to find out about how we can solve this problem. Okay, so yeah, go through this problem and have an idea about what the problem is saying and how to go about this problem. So in this problem, the flow through pipe has been the solution of Navier-Stokes equation. The exact solution of Navier-Stokes equation for flow through a pipe has been shown here. Okay, so what happens in this? Consider a flow of oil with density 894 kg per meter cube and mu 2.33 kg per meter second. In a 28 centimeter diameter pipeline at an average velocity of 0.5 meters per second. A 330 meters long section of the pipeline passes through the icy waters of a lake. Disregarding the entrance effect, determine the pumping power required to overcome the pressure losses and maintain the flow of oil in the pipe. So this is the for this we have to make a few assumptions before we reach this expression from the Navier-Stokes equation. For so this is the the exact solution of Navier-Stokes equation. Okay, now for this we are considering a steady laminar incompressible and fully developed flow. So if we use these assumptions in the Navier-Stokes equation for flow through a pipe, then we will reach the condition, that is the velocity profile through the pipe as this: V equals to 1 upon 4 mu minus dp by dx, or z, let's say z, r square minus r square. So like this is the pipe line. Okay, this is the center point, center line, and this is the direction of z. This is the direction of r. So at any point small r, the velocity is given by this value. Okay, it is equal in the azimuthal direction, that is with the change in the angle, that is throughout this circular region, which are all at a radius r, the velocity will be same. Okay. This is called the Hagen-Poiseuille flow. Now with this, if we try to find out what is the u average velocity, that is the average velocity here will be, or so Vz average, if we take the average over the area, we will get it as r square by 8 mu minus of dp by dz. Okay, and therefore this is the value of Vz, and what is the value of the what is the value of the discharge? Okay, what is the value of discharge? So for that we have to take this is the value for V average velocity, so and the value for discharge. So discharge is equal to integration 2 pi r dr. So we are taking the area of this differential element and we are taking the velocity in this direction. Okay, so area multiplied by the velocity will give the volumetric flow rate. So if we integrate this, putting the value of Vz, and if we integrate this, we will reach the value as pi r to the power 4 by 8 mu minus of dp by dz. Okay, and so from here we can also write the value of q with respect to Vz, that is equal to pi r square into the average velocity. So this is just the total area A of the total cross-sectional area of the pipe multiplied by the average velocity will give the average discharge through the pipe. Okay, now from this equation we have to find, we have been asked to determine the pumping power. So the pumping power is what? Is equal to actually the pressure difference multiplied by the discharge rate. What is the pressure difference? We have got that the U average velocity is equal to uh, r square by 8 mu r sorry r square by 8 mu minus of dp by dz. So in the direction of z, pressure is decreasing. So that is why this negative sign is coming. So if we write it as p minus 0, but p is actually, p will be at 0 and 0 will be at z. Okay, so p minus 0 and 0 minus z. So basically our delta p and 0 minus z will be, say, L, 0 to L. So L or minus of L. So minus and minus. So this minus is being taken care of here. So what we get here, it is r square by 8 mu delta p by L. So delta p can be written as 8 mu Vz average r square by r square. Okay, 8 mu uh, Vz average by r square. And but we have been given the diameter, right? 28 centimeters. So this is just r in terms of d if we write, so it is d squared by d by 2 whole square. So 4 by 4 there will be, so it will be 32 mu Vz average by d square. If we just put the values, 32 multiplied by, what is the viscosity? Viscosity is 2.33 kg per meter second. 2.33. What is the average velocity? Average velocity is 0.5 meters per second, and d square is 28 centimeter diameter, so 0.28 whole square. Okay, so if you just calculate it, we will get it as 156,918 Pascal. And this discharge Q is equal to pi r square into Vz average, or pi by 4 d square into Vz average. So this is pi by 4 into 0.28 whole square into 0.5. So this comes out as 0.0307 meter cube per second. Therefore, the power required is delta P into Q dot. This is 156,918 multiplied by 0.0307 Pascal into meter cube per second. So that is joule, actually, joule per second, or watt. So this is actually 4831.13 watt, or this is nearly equal to 4.83 kilowatt. That is option number D. Okay, so I hope this is clear to you. If there is any doubt in this, you can ask. Okay, so we're moving to the next problem for this. Okay, so yeah. So a Newtonian fluid flows slowly under gravity along an inclined flat surface that makes an angle theta with the horizontal plane as shown in the figure. The film thickness is T and it is constant. The flow is two-dimensional. Nu is the kinematic viscosity. So we have been asked to determine what is the velocity u of the flow along the x direction. So writing the x momentum equation, writing the x momentum equation uh, with constant mu, we are writing the Navier-Stokes equation for a constant viscosity mu. We will get the form as rho dui by dt is equal to rho gi minus del p by del xi plus mu del 2 ui by del xj2 plus 1 by 3 del by del x psi del dot u vector. Okay, now we assume steady flow and a steady and incompressible flow we are assuming. Assuming steady incompressible flow, this equation will become rho. So for steady state and for steady incompressible flow also, and as you can see, and for fully developed flow, and wait, so we are assuming steady incompressible and fully developed flow. Compressible and fully developed flow. Okay. So for fully developed flow, this del u by del x will be equal to 0. There is no change in the u with respect to x. Also del v by del y is equal to 0, and v is equal to 0 at the wall, that is this wall. At this wall v is equal to 0. Okay, so therefore v is equal to 0 throughout. Therefore this term du by dt, okay, that is this one, this is 0 for steady, plus u del u by del x, this is also 0, plus v del u by del y, this is 0. So this term is totally 0. Okay, so this term is totally 0. This term is totally 0. Now for incompressible flow, del dot u will also be 0. Also del u by del x and del v by del y are 0. So that is del dot v is also equal to 0. So even if it is not incompressible, it is by default becoming incompressible here. Then since both the inlet and exit are exposed to atmosphere, so del p by del x will be equal to for this one will be equal to 0. Actually this becomes equal to dp by dx, since del p by del y is nearly very less than del p by del x. This we get from the ordered analysis, which we are not doing here. This is dp by dx, and this is, that is p2 minus p1 is by whatever be the length. So this is 0, since p1 is equal to p2 is equal to p atmosphere. Okay, therefore this equation, so the left hand side becomes 0, and so we will only be left with 0 is equal to rho gi. What is gi? This will be g sine theta in the x direction. Okay, g sine theta in the x direction, and dou p by dou x becomes 0, plus mu del 2u by del y2, this is equal to, this is becoming 0. This implies del u by del y, del 2u by del y2 is equal to minus of rho g sine theta by mu, or g sine theta minus g sine theta by nu. Okay, so if we solve it, del 2u by del y2, so del u by del y is equal to minus g sine theta by v minus minus g sine theta by nu into y plus c1, and u of y is equal to minus g sine theta by nu into y square by 2 plus c1 into y plus c2. At, now we will put the values. At y is equal to 0, u is equal to 0. This implies c2 is equal to 0. At y is equal to the thickness t. At this thickness t, as a boundary layer has developed, so for this flow, as the boundary layer has developed here, the u is not changing with y anymore. That is, del u by del y becomes 0 at this thickness t. Okay, so at t, del u by del y is equal to 0. That is, c1 is equal to g sine theta by nu into t. Therefore, ut is equal to g sine theta by nu ty minus y square by 2. So this is the required expression, which is option number C, which is option number C. Okay. Now what is the average velocity? For average velocity, what we have to do, u average is equal to integration u dA by the total area. This is the area average. So integration from 0 to t u into b dy. B is the depth into the paper that we are considering, and b into t. Okay, so b gets cancelled, and this because it is constant and not equal to 0, and so if we integrate it, we will get g sine theta by nu into t, and we are integrating ty minus y square by 2 dy from 0 to t. So if we integrate this, we'll get it as g sine theta into t square by 3 nu, which is option number B. And for the discharge volumetric flow rate, Q is equal to just integration to T du dA. So this is just what we have got here, that is U average into area. And so what is U average? U average we have got as g sine theta t square by 3 nu, g sine theta t square by 3 nu into what is the area? Area is B into T. So it comes out as G per unit. So B is equal to 1. So G sine theta into T cube by 3 nu, which is option number C. Okay. So I hope this is clear to all of you. If there is any doubt, you can ask. Else, if there is no doubt, then we will close today's session. Okay, so if there is no doubt, then we are closing today's session. Thank you for joining, and see you in the next class.